we proved that what happened? We proved that for chi, if a character of z is star is bounded and it is multiplicative. Therefore, this product formula holds. And now I gave a heuristic how the proof will be completed from here. Basically, by taking log of this, uh, so the point was to take log of this, which is the sum of these logs, where only the first and this log you expand in power series and only the first term is dominant. So basically, as s goes down to 1, this remains bounded. The rest of it remains bounded as s goes down to 1 because of the square, cube and all that. So it's only chi of p over p to the s, and the divergence of summation chi of p over p to the s as s goes down to 1. By divergence, I mean whether blow up of this quantity as s goes down to 1 is equivalent to L chi of s being either blowing up to either infinity or 0 as s goes to 1. It doesn't blow up to infinity, we know. L chi is convergent for all s positive. Therefore, it's continuous and continuous there because of uniform convergence. So the only problem could be that it blows up to 0. So that was one of the things. And so the other thing was, the key point was to show that L chi of 1 is not 0. Okay, so that was these are the things. So the only point here is that, well, there are these 2 points. So how to take log of complex numbers. So this was somewhat formal. And the other is to show that these non-trivial L functions don't vanish at 1. Okay, that is all we wanted to do. So these are, once we do that, then I will just put together and we'll see again this argument is valid. So in towards that, we were first studying the logarithm, and on the disk of radius 1 around the 1, actually you can define it on the whole. Okay, so this power series definition is only on this disk. So you take the disk 1. So we are looking at numbers which are 1 plus z, where z has absolute value less than 1. So that will give me this disk. So for such a number, log z is defined, its power series around 1 is defined in the usual way. Okay, you take the usual power series which you have used in 0 to 2. You use the same power series on this disk and it converges and defines a nice function. Okay, it converges and uniformly in any strictly smaller disk. The claim was that the exponential of this is a log, in the sense that actually I forget now, I should fix this. Is it plus or minus? Okay, when we take, okay, so log of z is 1 plus z minus 1. So that will give me, okay, sorry, I didn't, I forgot about this, but I would not, I would like to fix it so that there is no confusion. So what log of 1 plus x is x minus x square plus that, which is actually minus 1 to the k minus 1 x to the k over k factorial. 1 to infinity, sorry, k. There is no factorial, it is just k. Now that means log of this should have, so this should have been z minus 1 to the k and minus 1 to the k minus 1 divided by k. Okay, I have put the minus 1 to the k into it and called it 1 minus z to the power k. So then an extra minus remains. So this does remain. Okay. So log z is negative of this 1 minus z to the k over k, sum k equals 1 to infinity. For those who understand complex logarithm, I mean, if you have done basic course in complex analysis, you know, this is the principal branch of logarithm we take. I mean, so it is the, so log can be defined here uh, up to, so the choice of argument is the problem, but is this the one which is real on the real line? Okay, when z is on the real line, this will be a real number. Okay, it could have been the real number plus 2 pi I also, but that is not the one we are choosing, but we are choosing the one which is real on the real line. So that's the branch of logarithm. Anyway, so I will leave this exponential of, so here again there is a minus exponential minus 1 minus z to the k over k, that is z. So this I left as exercise, and what I said last time was correct. it is indeed you can do it by differentiating and so on. So there you can also use the power series of exponential and expand the whole thing and cancel terms to see that this is what remains. That leads to basically an inclusion exclusion like formula. When you expand this, see this is already, so each 1 minus z to the power k you can expand in powers of z. Okay, and exponential of this can be expanded in powers of this. So you do a full expansion in powers of z, then only the first coefficient remains, everything else cancels. There is basically some cancellation of all the z square, z cube, z power 4, it's all those coefficients, and that will be some kind of inclusion exclusion only. Other option is to take 1 by z times this, or exponential of this times z. So let me just indicate and leave this as exercise. So with two options. Option 1, find power series expansion of the left side. In Z. Okay. Option 2, you consider this quantity times Z. So in other words, I bring this to this, I have to show it is equal to 1, differentiate and show that it is constant. Okay, differentiate, show it's constant, and reduce the constant is 1. So those are two ways in which you can do it. I will not do it. Okay. Okay. So then log of so this defines logarithm on this disk, and that is sufficient for us because we want to define logarithm of 1 minus chi p over p to the s, which is chi p over p to the s, you see, is going to be of absolute value less than 1, right? So chi p over p to the s is strictly less than 1 for all s positive. This has absolute value 1, this will be bigger than 1, so that is fine. So 1 minus that will remain in the disk of radius 1 around 0, okay, because that is at most 1. So minus log of 1 minus chi p over p to the s is well defined and given by this. So I have taken this minus on this side, so it will be 1 minus this will be chi p over p to the s to the power k, that is chi p to the j over p to the js times j. So this is the series, and this is how it is defined, okay. All right, so that was the just the recap, and now what I wanted to say was this lemma. This lemma that if you take these logarithms, yes, each individually e to the minus this will give me. So the claim is that if you take this, you will get L chi of s. Okay, so this is the claim, and actually the answer is easy because you can exponential is okay. So the proof is. Do I take a minus log here? Yeah, that's right. So yeah, we take e to the minus log. So the left side is product over p e to the well, let me write it like this. Instead of writing like this, let me just write it as okay, sorry, what is it that I want to say? Yeah, no, that inverse is not there. Okay, actually, sorry, once confusion. Yeah, 1 minus chi p over p to the s is inside this disk. I have defined logarithm of that. I have not defined logarithm of the
So we want there minus of log.
Yeah, but if I put minus of log, right, so I don't write it as log of this inverse because that point, that number is not here, right? 1 minus that inverse is not here, I guess. Or is it? No.
It may not be there, probably.
Uh, yeah, 1 minus z inverse will be okay. So if will 1 minus z inverse is 1 plus.
I mean, the magnitude may be too large. If the magnitude of something is small, then once you invert it, the magnitude will be too large to be in the disk.
That's right. But if mod z is less than half, then this is actually okay, right? If mod z is less than half, then this whole thing is absolute value is less than 1. In such a situation, it is okay. Is that correct? I mean, so then it will be then this is inside the disk. If mod z is less than half. For mod z bigger than half, you're right. It is not. So if mod z is bigger than half, this 1 minus z inverse is not inside the disk. 1 minus z is, but 1 minus z inverse is not. Yeah, so maybe then I get into a little bit of trouble here. This one, when s goes down to 0, it can be close to 1, right? So, oh, sorry, we are not we are going to take s bigger than 1. Ah, okay, okay. So then I'm fine. Okay. So, okay, so before, yeah, so all this claim is fine. So, but maybe I make that, I state that properly. So we are going to stick with s bigger than 1. So, okay. So actually there is a point I thought now I made a mistake and I'll get stuck. But let's note that if mod z is less than half, then 1 minus z inverse, this whole thing z plus z square, etc. is bounded by half, right? Oh, sorry. By bounded by what? Half plus half square. No, that will go up to, this will be upmost 1. This will be at most half plus half square plus dot dot dot, which is 1. So this whole quantity, if mod z is less than half, then this is okay. Hence, for s bigger than 1 and for all p prime, we know that chi p over p to the s is going to be smaller than 1 by 2, 1 by 2, 1 by 2 to the s, because every prime is at least 2, which is strictly smaller than half. So this is okay. Therefore, log of 1 minus chi p over p to the s inverse is well defined. For s bigger than 1. Is this okay? So you see, it is not, it is one, since we have defined logarithm in a very specific way, it is not okay to just call it minus log of that. I mean, that is, one has to be careful. Log of this quantity is also well defined. Now, so, or rather, I could have stated it a bit more generally here. So from here, what I mean is that for mod z less than half, log of 1 minus z and log of 1 minus z inverse. Okay, that doesn't look proper. Let me write it. Are both well defined, and negatives of each other. So I will leave that also as exercise. See, the only definition of log is this. If you want to do it from the definition, log 1 minus z is defined by this, z minus z to the k over k. Log 1 minus z inverse is, you will have to write it as 1 plus this whole thing. So you'll get this whole quantity to the power k over k, sum over k. You have to do all that, and then you will find that they are negatives of each other. Is this okay? So now I will write the claim that, so the claim is e to the power of sum of log 1 minus chi p over p to the s inverse sum over p is equal to L chi of s. For s bigger than 1 and any character. So now let's prove this. I mean, it's the proof. Actually, here I'm trying to shortcut something in Stein and Shakachi. So it is quite likely that I have made a mistake. Okay. It looks like I can shortcut a little bit what they have said, but most likely I have made a mistake. So I ask you to please be critical in looking at this if there is a gap. Yeah, anyway. So not just in this proof, but in how it is applied. Okay, so this one, what we get is, I mean, so exponential is okay. E to the sum of p is product of the exponentials. Is product over p e to the log of 1 minus chi of p over p to the s inverse, which is product. So since this is inside that one, e to the log of that will give you exactly the whatever that quantity is. Namely 1 minus inverse, which is in fact L chi of s. Okay. So this is okay. So how is that going to be helpful? Any questions so far? Is it okay? All right. So then let me go back here. So how am I going to use that? The point is, I want what is it that I want to do? I want to use the log to do this business, that I want to relate the divergence of chi p over p to the s with log, right? So let's do that now. Now I can do that because now what? Let me put, so here starts a paragraph. So we have written L chi of s as e to the power of sum over p log of 1 minus chi p over p to the s inverse. Now I will use the fact that this exercise here, that log of the inverse is minus of the log. Okay, and then this is by definition a power series. So this is e to the sum over primes. And what is this going to give me? Minus log of 1 minus chi of ps. I have written here chi of p to the j over p to the js with a j. So here I have j equals 1 up to infinity. Okay, so let's take the exponent. Let's look at the exponent. It is first we write the sum over j equal to 1. Okay. Well, you can actually, okay, is the interchange justified? This is something one has to worry about. Chi of p to the j over this is j greater than equal to 2. Okay, so how did I interchange the sum? Is it okay? Yeah. Yeah, s is bigger than 1. Yeah, s is bigger than 1 and summation 1 by p to the s is summable. I guess, is this absolutely summable? Just hold on 1 second. So there's somebody at the door. Sorry. Hello. Oh, so yeah. So is this okay? The sum is it absolutely summable or not? This one. Okay, let me complete it and come back to this. I didn't think of this issue also. So this one, this whole thing. So this is bounded in absolute value. Bounded by sum over j greater than equal to 2, sum over p, and I can just put 1 for that, j times p to the js. Okay, so that is actually, yeah, I didn't have to interchange. So anyway, so this is actually, yeah, p to the js. If I sum over j, what do I get? I mean, so this, sorry, this is j greater than equal to 2. So summation 1 by p to the js, j greater than equal to 2 will give me 1 by p to the 2s, comes out, and then what is it? 1 plus 1 by p to the s plus 1 by p to the 2s. So it is 1 over 1 minus 1 by p to the s. Okay, so something like this. So, and then I sum this over primes, right? So this is actually, or this is 1 by p to the s into p to the s minus 1. And then you have to sum this over primes. So this is actually sum over primes of 1 by p to the s into p to the s minus 1. But that is like, okay, p to the s minus 1 is at least half of p to the s, right? If you subtract 1, you can't be smaller than that. So this is like, this is more or less like sum over p. This I'll say bounded by a constant over p square.
Sir, there was this J, right? That we didn't take.
Yeah, I didn't even use that. Maybe it's not even needed. You can use
No,
it. Yeah, I did not use it actually. I did not. I just, because that one will only make it more complicated. Yeah, if I use that, I would get log actually. Yeah, actually, maybe I could have done that also. Well, but there is j summing from 2 onwards. It's not exactly log. It will leave out something. Yeah. So if it was j from 1 onwards, this sum would be exactly like a log of 1 minus 1 by p to the s. Yeah, I could do that. Yeah, you are right actually. So I could have done that also. But I just removed the j and just summed this. That gave me 1 by p to the s into 1 by p to the s minus 1, which is approximately like p to the 2s, which is smaller than p square. So this whole thing is bounded by, even as s goes to, even for all s, uniformly bounded by a constant over p square. So in other words, so this quantity is big O of 1. Okay, it does not blow up because the uniform bound I have found does not depend on S at all. It does not blow up. Okay, so that's what we get. So now if L chi of 1, so consequently summation chi of P over P to the S blows up, or blows up may be a bit misleading. It is complex valued. Okay, so let's write stays bounded as S goes down to 1 if and only if. See, what we have is here L chi of S is this plus. So what I have, okay, maybe I just write like that. So what I have done so far is that L chi of S is e to the sum of chi of P over P to the S over primes plus some quantity that stays bounded as S goes down to 1. Okay, this big O of 1 as S goes down to 1. Therefore, the blow up or not blow up of this depends on whether this is 0 or so for this to become 0, this has to blow up to minus infinity. For this to blow up to plus infinity, this also has to blow up to plus infinity, right? So this one stays bounded as S goes down to 1 if and only if L chi of 1 is not equal to 0 and not equal to infinity. Okay, is that okay? So this is equivalent to that. So this is the key thing I wanted to deduce here, right? And now with the application of logarithm, I have managed to do it, that relate the divergence or non-divergence of chi p over p to the s sum to the vanishing non-vanishing of L chi of 1. We know that this doesn't happen. Anyway, this is ruled out. Or rather, ruled. Okay, what is ruled out? We already know, actually. We know that L chi of 1 is actually not infinity. So this one we know. Since it converges for S bigger than 0. So this is fine. It is this is the questionable thing. So this is what I need to do.
So just remind me again, we are dealing chi here is trivial character or the.
Oh, okay. Sorry. No, this is true. This is irrespective of everything too. But this is for the trivial character. This is not going to be true. So what we need to show is only that this doesn't blow up for non-trivial characters. Okay, I will recall that why that is the case, why that will give ultimate, but that is because let's go back. Where was that? Maybe in the previous page or.
I think it's a bit below that, maybe. Be in the same page, probably, right? I think you wrote it in the previous.
Here, you mean?
Move down. Yeah, so look, maybe here somewhere.
Okay. Yeah. No. For the so here I have shown that for trivial character it does blow up as S goes down to 1. I have shown that. Okay, so but I mean, just I'm trying to show you the case where that was relevant. So the point was summation 1 by p to the s has to because just writing indicator of the arithmetic progression in terms of characters, we got that it is this one which is the trivial character chi naught p over p to the s and a finite sum consisting of chi p over p to the s over non-trivial characters. So to show divergence of this, our idea is to show divergence of this and non-divergence of all this. So there cannot be any cancellation in the divergences. So this will diverge, that I have already shown. I have to show these things don't diverge. So as you said, what we want to show is that this as written it is okay, but we know that this is not going to be true for non-trivial for trivial character. This is this does. Oh, okay. Sorry, here you meant. This is okay. So now I see what you meant. So here I should say we know this for chi not equal to chi naught. For chi not equal to chi naught, we know that it doesn't blow up to infinity. And we also will want to show that this is true. And for chi naught, it does blow up. And as I showed earlier, summation 1 by p to the s is related to these two things. So once we are done, that will do it. Okay, sorry. Any questions, or did I make it clear? Or?
Yeah, so for chi naught, it was that except for finitely many terms, that will be 1, right?
Yeah, exactly. So
Okay.
it is more or less like the, no, not finitely many terms, for all primes that are co-prime to, sorry, yeah, that is finitely many terms. Is that right? 1 second.
Yeah, except for the ones that divide D.
Except the ones that divide D, it is fine. So the rest will blow up. Yes, exactly. Yes. I just rewrote that again here fully. Yeah, log zeta of s is like this. Yeah. Yeah, it is like summation 1 by p to the s over all primes, and that also by relating it to the zeta function, I was able to show it diverges. I didn't need this extra complex logarithm there because everything was real valued here. So I could use the usual log. And when I went to the non-trivial character, I had to, that's what I tried to imitate, but I had to introduce complex log. That's all. Is okay? Any other questions, comments? Okay. So then let me just, this is the last remaining piece, that L chi of, so this is the part which I have slightly simplified from Stein and Shakachi. I mean, did you spot any gap? That is my question actually. Is this okay? So what Stein and Shakachi do is that they define, I didn't take the log of the L function itself here at no point. So what they do is they also define the log of the L function. Okay, and then show that log of the L function, how do they define the log of the L function? So just to say what they do, because I was very unsure whether I am making a mistake or something. So log of the L function in Stein and Shakachi, they define log of the L function as, see, formally what should its derivative be? It should be L dash of s over L of s, right? The logarithmic derivative. If you could differentiate, you should get this. So, but this is well defined, or rather they define it like this with a negative because s is at the bottom. So they go from infinity to s, so they define it like this. Okay, this is the definition. So before that, they have to justify that L dash exists. I only showed that L is a continuous function by uniform convergence. You can go one step further and show that L is in fact continuously differentiable. You just have to differentiate term by term and show that the resulting series converges uniformly. Then you get that L dash exists. And you have to show the decay of L so that this integral is convergent. And then you can define log L of s like this. And then then a further argument to show that log of L of s is actually equal to this exact thing in the exponent here. So somehow I thought that it is avoidable. I mean, I don't need it. It's all correct and important, but it's just for the objective we have, it is not needed. That's what it seems to me. Anyway, if you spot a gap, let me know.
Yeah, don't you need that for, so you had that log L chi s earlier, right?
Yeah, I wrote it like taking log L, but here in this argument, I didn't take log at all. I just left it in the exponent, right? I've written L of S as summation chi p over p to the s plus big O of 1. And from this, it is enough. This is enough to see that the blowing up or not of this is equivalent to vanishing or not of this, isn't it? So I didn't actually write log of L, is what I'm saying. Did I answer your question, Soumendra? I mean,
Yeah, I'll look it more carefully and then, yeah. Okay.
so it looks like, yeah. So maybe maybe I'm making a mistake. It's very unlikely. Stein and Shakachi, there is very few mistakes. There are actually. I have found one mistake, at least one. So, but it is very well written and has very few mistakes. So I mean, there is anyway no mistake. It may be just, but it's not a question of mistake. They are usually quite careful. So I'm wondering if I'm just being careless in something. So anyway, if you don't spot any error, then there is no error. Okay. So, okay, so that finishes the last remaining step. For chi not equal to the trivial character, chi is a character of ZD star. L function is not vanishing at 1. L chi of 1 is not 0. This is the thing we have to prove. So here, so how do you show this? Okay. So everywhere I see this is what is done, but again, so there is something. I mean, it's a bit strange. The proof in Stein and Shakachi and in Apostle is, in all proofs, it is the following. Okay, in all proofs I have seen, it is like this. So the lemma is so you consider the product of all these L functions. Okay, so this is greater than equal to 1. This is the way it is done in Stein and Shakachi and Apostle. Basically, this more or less finishes it. The point is the following. So here, so how does this help? Okay, I will prove a lemma which is slightly different. I am going to prove what take the proof from JP Ser's book. Okay, which is often quite tough. One has to fill in a little bit, but this one seems okay to me. Modulo one step, which I will ask you how to do. But L chi of S, this. So how does this help? See, L chi naught of S. So this is true for all S bigger than 1 is the point. But what we know is that as S goes down to 1, we will let S go down to 1. L chi naught of S is like 1 over S minus 1 plus something. So we got that as zeta tilde of S or something like that. Or maybe I write chi naught tilde of S, where this one is continuous on 0 infinity, right? And for L chi of S is continuous on 0 infinity for all chi non-trivial character. Non-trivial characters are continuous on 0 to infinity. So we are only approaching 1. 0 is here. So S is approaching here. So one of them blows up, the others don't blow up. Now the product is going to stay greater than equal to 1. Okay, so what can happen? So if one of them vanishes, okay, so if one of them vanishes, will there be a problem? That is the question. So if one of them vanishes, a approaches 0 as s goes to 1, which is same as saying L chi of 1 is 0. Okay, that's a continuous function. What is the problem? That the point is that this will not vanish. It is not simply vanishing. It will vanish like s minus 1. Times something, okay, is going to be like, since I mentioned just now that it will behave like the derivative of L chi at 1 times s minus 1. Since it's a differentiable function, L chi is not any continuous function, it's a differentiable function. So its vanishing has to be like linear at least. Or it could be a higher power. It could also be, this is correct anyway, the derivative could be 0, but at least it vanishes like 1 power of s, right? Now you see the product will have, this s minus 1 will cancel this. So that means then the product will be well behaved. What happens? Has no singularity at as s approaches 1. Okay, that so what? I mean, so we are not saying that it has a singularity. So this shows that has no blow up as s approaches 1. That much is clear. But we only have that this is greater than or equal to 1. So this does not contradict anything. One of the L functions, if two of them vanish, that would be a problem. 2 chi such that L chi of 1 is L chi 1 of 1 is 0 and L chi 2 of 1 is 0, then there would be a problem. Then product L chi of s would actually go to 0 as s approaches 1, right? Because one of them blows up like 1 over s minus 1, two of them vanish like s minus 1, so they will cancel and this will vanish like s minus 1. That would contradict that, would contradict the lemma. Contradicts the lemma because it cannot vanish, at least because we have a lower bound of 1. Is that okay? So what this lemma shows that is two of the characters cannot vanish. One of them could vanish in principle. Now, the thing is, this is okay. So this leads to two possibilities. So if chi is a complex character, that is, chi is not equal to chi bar. Okay, or in other words, okay, let me put it this way. See, so what we any questions about what I'm saying here? I am stating a lemma, which is the often proved one, that product of characters, L functions over all characters is greater than or equal to 1, and I'm trying to tell you how that would imply that no character can have vanishing at 1. I will not be able to tell it fully for a reason we'll get to. And the point is that one of these explodes like 1 over s minus 1. So if two of them vanish, they will vanish like s minus 1. So the product would vanish at least like s minus 1, contradicting this. So you see that two of them cannot. But point is, if L chi of 1 is 0, then chi bar is also a character, and L chi bar of 1 is also 0. Chi bar is just the conjugate. You see the L function for chi and L function for chi bar will be conjugates of each other. So if this vanishes, this also will vanish. Okay, L chi bar is just the L function conjugated because you have chi of n over n to the s, right? You just conjugate. So if one of them vanishes, it looks like both of them vanish, and that would be ruled out by this. But one problem is that there are characters chi which are real valued, in which case chi is equal to chi bar. So this, what this shows is that hence no complex character can vanish. Equal to 0. Here complex means chi not equal to chi bar. So it is this real valued problem is with the real valued one. What if chi equal to chi bar and del chi of 1 is 0? There is no contradiction straight away because one of the characters vanishes, one of them blows up. The product is still continuous, but it may stay above 1. Who knows? So it requires a longish argument. It requires an argument. Okay, so this is one approach to showing that L functions don't vanish. So this is the approach taken in. This is the approach in Stein and Shakachi, and also in Aposto. So I have seen this in many cases. They divide into the complex character and real character case, and so give us different, somewhat longish argument. It's not as simple. It's a little involved argument that even one real character cannot vanish. Okay, so is that okay? Is that clear? I mean, so I wanted to just give you an idea of what this is like. I will not use this lemma. We will use the product, but we will use a more precise representation. I will give the proof from JP Sir's book. So we will use a different lemma. So we will take so here the lemma is slightly more precise. So this is equal to what? He calls this is equal to, okay, so it is equal to another function, product over primes of, I'll have to look up 1 second. So it is, so this is P that don't divide D, P that don't divide D. It doesn't look clear what I have written. So this product is over.
Sorry, I just want to understand this real valued characters. That means what? They have to take. So is that the ones that are of order 2 or?
Yeah, do they necessarily have order 2? Maybe. So they do exist. So they take only values plus minus 1. So yeah, then definitely they would have order 2. Yeah.
So that's the only one. Okay.
But it's not necessarily. I think it's so when so when n is 4, for example, you have 1, right?
Correct, but I'm just asking like those are the only ones then you have to understand. So it's basically like changing signs in the sum.
Right, but it's not. But there can be multiple characters which are real valued, I think.
Okay.
Because this ZD star is not a cyclic group. Okay, it can it can be a product of 2 cyclic groups, let's say. So from each one you may have one real character, right? I mean, so if it was ZD itself, I think there's only one possibility, I think, maybe. +1 -1, then you have to take that. But here it can ZD star could be a product of the form product of Z2 times Z2. It could be isomorphic to that. In which case you can take one real character here, one real character there, and take the product also, tensor product. So there are multiple, there can be more than one real character. I think when D is 8, for example, there are at least 2.
Okay. Okay. Thanks.
Is okay? Yeah. So it's not exactly one real character. There can be more than one. That's all I meant. Yeah. So chi p, so L chi, so it is the product over all primes that are co-prime to D. That is those that don't divide D. Okay. 1 minus 1 by p to the s times f of p. I will define what is f of p, whole raised to the power g of p. I have not defined f of p and g of p, where f of p is the order of p in ZD star, and g of p is the size of ZD star divided by f of p, which is the Euler quotient function phi of d. Let me write properly. It is phi of d divided by f of p. Okay, so what is this? This is actually the smallest exponent. I mean, so smallest power such that p to the f of p is 1. Okay, in ZD star. So in other words, that is, it means it's congruent to 1 mod z. That's what I mean. So it's the smallest power, f of p is the smallest power such that p to the that power is congruent to 1 mod d. And g of p is the size of the group divided by that. So if you know, this is the size of the subgroup generated by p, and this is the quotient of that, size of the quotient of that. So that's what this is. So this formula is there, and what Z does is deduce it from this formula. Okay, so this is a more precise looking formula than this. You see that this is bigger than 1, right? Everything here on the right side, left side, you have you're multiplying complex valued things, but because of conjugate pairs and so on, this is actually real valued and positive. In fact, you see this is positive. Everything is positive, and everything is bigger than 1. You have 1 over 1 minus something. So everything is bigger than 1. So this lemma is stronger than just writing greater than equal to 1. So it's a more explicit form. Okay, so how does this lemma help? So maybe in the remaining 2-3 minutes, let me tell you how this lemma helps. For all chi naught equal to chi naught from here. From this lemma. Okay, so again, the point is one of them, L chi naught is actually, so again, L chi naught of S is like 1 over S minus 1. I mean, in fact, let's write it as 1 over S minus 1 plus, what is it? I had written some symbol for that. Zeta tilde of S, where this is continuous on zero infinity. And L chi is all L chi for chi naught equal to chi naught are continuous. On zero infinity. So what happens is that so this one actually, oh, hold on. So there is this issue. Yeah, so okay. So anyway, so this thing is actually stated for S bigger than 1 only. For S bigger than 1. Okay, so L chi is continuous. So now suppose L chi of 1 is 0 for some chi. Actually, more or less, I didn't have to repeat. Everything is the same as what I wrote here. So then, what this would imply is that the product extends continuously to 0 infinity. Okay, so because one of them is exploding like 1 over S minus 1. So first of all, this actually implies that L chi of S is like S minus 1 times L chi derivative at 1. And that implies from there, the vanishing is at least of order 1. And that cancels this, and the product will be well defined. So you'll get a continuous function on 0 to infinity, right? The product will be continuous on 0 to infinity. Now what says, okay, I will have to maybe come back and explain this next time. So, but that can't happen. Problem is, this right side does not extend continuously. Okay, but the point is, but the right side does not extend continuously to 0 infinity. In fact, it blows apart
It's 1 o'clock.
Okay, I will just stop with this. Blows apart S equal to 1 over phi of t. Okay, we will show that this right side blows up when S is equal to 1 over phi of t. Now, this side extends continuously. Okay, this I have to see. I actually ignored this point. Now I have to see. This is true. Does that mean this is true for S bigger than 1? So this does not extend all the way to S equal to 0. Does that mean this also does not extend all the way to S equal to 0? I mean, what we are saying is, okay, actually this actually blows up. Okay. So these two are equal. Okay, I think here I may have to invoke complex analyticity. Otherwise, I may have trouble. Okay, so now I see what is the why Stein and Shakachi do this full proof. I mean, everywhere it is done. So if you want to entirely avoid complex analysis, you have to go this way. Here, if to get a contradiction out of this, okay, so the left side does not extend to 0 infinity, the right side doesn't extend. Where is the problem? That involves a little bit of complex analysis. Okay, maybe if so anyway, I will have to finish it next time. Maybe I will even tell both ways of doing it. Okay, sorry, I went over time, so I'll stop here.